Welcome to Physics Made Easy channel. The next logic gate that we are going to study is AND gate. We have already done with OR gate and now we shall study AND gate. In case AND gate can have any number of inputs, first of all, it can have any number of inputs and but only one output, same as OR gate. It gives high output. Output is high, that is output is 1 if inputs A and B both are high, or if all the inputs are high, then and only then output will be high. Output will be low even if one of the inputs is low. Again listen, output will be high if all the inputs are high, that is output will be 1 if all the inputs are 1. And output will be low even if single input is low. Now let us go through its truth table and symbol. Things will be more clear. And this is output is 1 if input A and B are 1. Boolean expression y is equal to A dot B. Logical symbol, this is the these two are the inputs and y is the output. We have got one straight line and then these parallel lines and then a curve like this, and then we have got output. Now let us focus on its truth table. Expression, remember this is y is equal to A dot B. Now De Morgan's law, if we apply De Morgan's law as I have said previously, this can be written as one expression is this, and resolve this just when doing De Morgan's law. I have written this expression A plus B, this whole bar, this is A double bar multiplied by or and B double bar. Double bar is just equal to the symbol we have already done in the previous lecture. This is A dot B. This is another representation of AND gate. Representation of AND gate in the form of AND operation. This is representation of AND gate in the form of OR operation. We shall do it extensively later on. Now let us focus on this. Both the inputs are low, output is low. One input is low, this input is low, this input is low, it means output is also low. And now this is high but this is low, it means output is 0 or low. Both inputs are high, note it down, this is 1 and this is 1 and this is output is 1. Output is 1 if all the inputs are high, otherwise output is 0. This is the DARD implementation, which I will skip for the time being. I will give you this representation, switch representation of AND gate. Now we have two switches in series. Two switches in series represent AND gate and two switches in parallel represent OR gate. And now even if if both A and B they are closed, then and only then bulb will glow. If either of them is not closed, then bulb will not glow. This is what is the essence of AND gate. If all the inputs are high, then and only then output will be high. Here, if both the switches are closed, A and B are closed, then and only then bulb will glow. Now, an interesting fact here is waveform. This is the waveform. Note down the waveform. Now, this is very much important from your examination point of view, waveform. Now, here in this section, input is 0. Input is 0. Both the inputs are low and output is 0. Here, one input is 1, but other input is 0 here. In AND gate, if all the inputs are high, now this input is high but this input is not high, it means output will be 0. We know that output will be 1 or high if and only if all the inputs are high. Now at this point, A is still 1 and B becomes 1. In this particular cases, both the inputs are high. This is also high and this is also high. It means output will become high here and it will remain high up to this point. At this point, what happens? B input is 1, but A input has turned out to be 0. Here it is 0, here it is 0, here it is 0. It means up to this point, output will be 0. So up to this point, output is 0. Why? Because input A is 0, low, and output will also be low. And at this point, when this becomes 1, A becomes 1, then B becomes 0. As B becomes 0, 1 into 0, one of the input is 0, it means output will be 0. Here again, B becomes 1, but A becomes 0. And here again the output will be low. So we have got these cases, here the output is low. So this waveform representation is very much important from examination point of view. And the next gate that we shall be doing is the NOT gate. NOT gate is the simplest gate. This is the simplest gate. It has got one input and one output. It gives high if input is low. It toggles, it reverses the input. If input is low, then the output will be high. If input is high, then the output will be low. Now it's symbol. Symbol is a triangle followed by this bubble. Now note down the difference. A filled circle gives us input or filled circle gives us output. Unfilled circle is a bubble. And here the Boolean expression is y is equal to a bar. Truth table is quite simple. Output is high if input is low. Input 0, output 1. Input 1, output 0. It just reverses the input. Now there is a transistor representation of NOT gate. We know it very well that the common emitter transistor, it is in common emitter transistor, input is out of phase with output. That is, this common emitter transistor can be used to represent AND gate. This is common emitter transistor. It can be used to represent NOT gate. How? Because if the input is like this, then the output will be out of phase. It will be like this. If this is input, then this is output. Input and output, they are out of phase by 180 degree. So it means that input is reversed by the common emitter amplifier. If I take input here just like this, then the output here will be taken like this. So it means there is a toggling or reversal of the input. And this is what NOT gate does. And now we will do switch implementation of NOT gate. This is a parallel circuit. Now switch is in parallel with this bulb. Now when this switch is closed, this wire will provide zero resistance path and no current will flow through it. It means when this is high, high means when switch is closed, bulb will not be glowing. And when this input is 0, that is this is open, then whole of the current will flow through the bulb and it will be glowing. Now its waveform is also very easy. This is its waveform. We divide whole period of the wave into small intervals 0 to t1, t2, t3, t4, and here in this phase the input is 0. As NOT gate just reverses the input, it means output is high in this phase. Here input becomes 1, here it is 1, here it is 1, and here it is 1. And up to this point, output will be 0. Again I will repeat that NOT gate just reverses the input, and here input becomes 0. At this point input becomes 0, so output is expected to be 1 in this region, and here it again becomes 1, and there is a bit of misalignment. Here it again becomes 1, and then it becomes 0. Simple logic: if input is 1, then the output will be 0. Here input becomes 0, and this there is a bit of mismatch between T5 and T6. You can just correlate these like this. So now we have done with the NOT gate. In the next, by combining these and this NOT gate, we make NAND gate. NAND gate is a combination of AND and NOT gate. Here is the symbol. We have this symbol is for you can say AND gate, and we have just attached this NOT symbol with it. So here A and B, here ANDing, that is multiplication of these inputs takes place by the AND gate AB, and here we just there is a toggling of this y is equal to A dot B. Now if I apply De Morgan's law is very useful and very simple, and if I apply De Morgan's law on and NAND gate, then it becomes A plus B. I will recall you the De Morgan's law. De Morgan's law say that A dot B bar is equal to A bar plus B bar, and in reverse it says that A plus B bar is equal to A bar dot B bar. So we have got these two forms of De Morgan's theorem, and I am applying this form. So this is another OR implementation of NAND gate. This is AND implementation of NAND gate. Remember these two implementations, they will be very much useful. And now we have combined these two gates to form this symbol. We have got this AND gate symbol and then a bubble. This bubble represents NOT. And here the output is y is equal to A dot B bar. Boolean expression, as I have already discussed, this is the Boolean expression. Here there is representation is in ANDing operation A dot B bar, and here this is in representation is in OR operation or plus, and here we have represented it by ANDing operation. A and D AND means A dot B. And now let us focus on its truth table. Its truth table says that simply when the input is low, output is high, because it just reverses the output of AND gate. When even a single input is 1, in this case, if this is 0, this is 1, here 0 and here 0. Output is 0 and this is again 1. And if all the outputs are high, then if all the inputs are high, then output is 0. Note down here the difference. AND gate says that if all the inputs are high, then output is high. Note down this. This is the AND gate. AND gate says that if all the inputs are high, then this input is high, this input is high, then the output is of AND gate is high. But NAND gate says that if all the inputs are high, then the output will be 0. This is the output of NAND gate. NAND gate. This is the output of AND gate. I will repeat. If the output is if all the inputs are high, then the AND gate gives us high input, and if all the inputs are high, OR gate gives us low output. If all the inputs are high, AND gate gives us high output. If all the inputs are high, NAND gate gives us low output. With these words, I finish this lecture. Kindly comment, share, and like this lecture. Thank you very much.